All right, troops. Next up is Newton's second law, and what I found historically that I can't depend on what's going on during lecture. I'm just taking a bite of my lunch. I don't have the camera going on so you can't see. So we're going to do a little intro to Newton's second law, and then I'm gonna show you a problem or a derivation. It's basically a little example problem, and what you're going to do is sketch out, write out the problem in your logbooks as part of your background and part of the pre-lab assignment. But right now, the next stuff doesn't necessarily have to go into your logbooks, and you should find it useful for lecture anyway. Okay, so I think we can understand that if you pull on something, it might accelerate, might move. Most of us, we don't experience too much the effect of acceleration when it's us pulling something. Mostly we experience it in a car, and we press the gas pedal and we feel some force, and we notice our speed increasing. In fact, a funny thing is, when I was a high school teacher, I did a lab with the kids where, excuse me, I brought in my rollerblades and all my pads and such, and then I had a spring scale, and one student would get all the equipment on, and another student would volunteer to pull on them while maintaining a constant number on the spring scale. And they're just always amazed. Within about a meter, 2 meters, they're already sprinting, trying to maintain that force. See, what mostly we do, if we're pulling some object, and what we do is we just pull hard enough to get it started. So yeah, it goes from some 0 meters per second to what walking pace? Let's see, half a meter per second, just to be safe. But actually, we maintain a constant speed. And so what happens is, this is a condition that we have our pulling force here, sometimes called a tension, and then there's some frictional force from this box scraping on the floor. And what we say is that if I sum the forces, if I sum all the forces as vectors, in this case, we have the friction. This is defined as F net. And what we find out in this case, that when we sum together F plus the tension, we notice that they would equal to 0, because if they're equal and opposite, remember, because that with vectors. So that means when the sigma F equals 0, then this is Newton's first law, and that just means if something's at rest, it stays at rest, or if it's moving, it just continues to move in a constant fashion, constant speed. And so to further understand this sort of sigma, and sigma just means, if I say sigma F I equals 1 to n, and I put I here, that just means F1 plus F2 plus all the way up to how many how many objects, and in this case they're all vectors, so we have to be careful. Although in physics 1100, it's usually pretty straightforward. So if you look at this example down below, and this is it's called a free body diagram with the real forces as opposed to components. But in this case, you see that we always have what's called a normal, not always. If an object's on a table on some surface, there's some normal force, so that's the table on the object. W is the weight, and that's defined as the mass times the acceleration of gravity. And hopefully you know what that is, either 9.8 meters per second squared or 10 meters per second squared. And usually we say that in this case, n plus w equals 0 because they're equal and opposite. You know, you put things on the table so they'll stay put. Now, in this case, you notice we're pulling with some force, and we're just saying that this thing is at rest. Or it could be moving. But let's just say it's at rest. So that means that in this case, F plus F equals 0. So there's no motion. Well, even if it was moving, it could still, so it's either at rest or it's moving at a constant speed. And we can just sort of say these equal to 0 because, remember, vectors are drawn to give you an idea of direction and magnitude. And yeah, maybe this one is slightly longer, but just make believe they're the same length. And then in the case here, notice now that F is greater than friction. So if I add these two together, it's not going to be equal to 0. And in this case, if I declare that this direction is positive, we can see that let's say sigma F, and we'll call that F of the pull. Friction, in this case, sigma F is not equal to 0, and not only that, sigma F is greater than 0. So that means in this case, if plus is to the right, that means you have a movement to the right. And in fact, if we now say that, in this case, say we got a hockey puck on ice, we just say that there is no friction. And we recall we did something like, we created ourselves a frictionless surface in Lab 4 using the air track. So in this case, sigma F just equals the force that I'm pulling with. So, and in fact, we sort of saw it because when we tilted the track, we saw something accelerating. We're going to do something a little bit differently here, where we're going to use gravity a little bit, but not quite the same way as Lab 4. But first of all, we just want to look at if we have some net force and we have some mass, and then we get an acceleration. Okay. And if we double the force, we double the acceleration. That seems pretty straightforward. And this is sort of like, we're not exactly proving anything. And one thing we're saying here now, directly proportional. So that means when F increases, A increases. And directly proportional means that 2 times F1 gets you 2 times the previous, they didn't give a subscript, but it gets you 2 times A1 if we call the original one A1. And if we have the force, so 1/2 F1 gets you 1/2 A1. Oops. So that's, say, directly proportional. F increases, A increases. F decreases, A decreases. And in direct proportion just means the same proportion. Okay. So then we also see now if we have some sort of mass, and I see what they're trying to say now. In this case, we have an acceleration, we have a mass, and let's say in this, we'll just say this equals to some F1. And let's see what the next one has to say. So now what we see is that, well, I'm going to explicitly tell you the mass of number 2 is equal to mass number 1. So then if we wanted to, let's see, I think that, yeah, we're keeping a constant force at the moment. So this still equals to F1. But because we double the mass, we end up with, notice there that A2 is about half. So if we double the mass, then we get 1/2 of A1 equal A2. And the statement of that, yeah, okay, so I didn't need to draw it. I put it on the next page. And that just means inversely proportional. So that just means that if for a given force, so this is, say, always going to be F1. So if we increase the mass, then the acceleration decreases. If we decrease the mass, then the acceleration increases, and in the same proportion. That's critical. It's what we call linear. There's no squared terms or something like that. And so basically we can get yet another one. If we put this, we see that, remember, M2 is twice M1, so now M1 plus M2 equals M3, and that equals basically M1 plus 2M1 equals 3M1. But then we would know that we know that A1 was from F1 over M1. So A3, if we keep F1 constant, now, so it's the same F1, so it's 3M1, and so we see that we can change this to 1 over 3 times F1 over M1, so then we see it's 1/3 A1, because this, we know, equals A1. So at the end of the day, that we say this is called Newton's second law. If you push on something, it could move as long as you're pushing, say, greater than the push or pull. Even it doesn't matter if you're pushing from left to right. You draw the diagram over here. It looks like you're pulling, but if you push on something, it could move. So that if this wasn't as long, let's say we had a force equal to friction, it still could move, but it would move at a constant speed. Now, and that means that the first situation is simply that at least sigma f is equal to 0. Now, if the sigma f, the net force, is not equal to 0, then it has a net force, and it will accelerate, always, always, always. And the amount of acceleration is directly proportional to the net force and inversely proportional to the mass. And note that A and F, are always parallel. We think about it where we have a scalar here. So a vector equal to a vector times some kind of scalar or divided by a scalar is still a vector that's parallel. So, and it's not F and A. You got to be careful. Any particular F is not guaranteed to be parallel. It's the F net. So you have to state that very carefully. Is parallel to whatever resulting acceleration is, and because when we increase speed or decrease speed, keep in mind it requires a push, right? So this guy here is changing direction at least, and remember, and hopefully you know that the velocity vector is always a tangent So it's changing direction. So it needs to be pulled over to the right. We don't know if it's speeding up or slowing down. So at best, we're going to say this is a right angle. And that would be either the force. We need a force, right? And it just so happens we should have learned that it's also related. It could also could be the acceleration. So they're always parallel. But it's F net. So then we just spell it out. And usually what we say is F equals ma. And so it's implied net force, but I know in physics 2100 we're always careful to write sigma F. I don't remember 1100. I haven't taught it in a while. But we always want to remember it's the net force. And then there's the units, kg meters per second. And 1 Newton is approximately the weight of 1 apple, which is kind of cool, right? So notice that we use masses in kilograms, right? Just a side note. In general, we say we weigh so many pounds. So it turns out that in our system, pounds are actually a force. But in metric system, pounds are a force, and which is cool, which is proper in the sense that weight is a force, mass times an acceleration. But we have a tendency to say we also weigh so many kilograms. So you just have to be careful about that in physics, that weight is a force, so it has to be in newtons, so we need our mass times the acceleration of gravity. So if I said, generally speaking, we make this conversion of 2.2 pounds per kilogram. So like you might say that if you weigh 220 pounds, you're 100 kilograms. But if you told somebody you had a mass of 100 kilograms, you actually would have a weight equals to 100 kgs times, let's say, 10 meters per second squared. So in reality, you really have a weight equal 1,000 newtons. But even Europeans, when you say you weigh 100 kilograms, they're imagining a weight of 220 pounds. So it's only in science that you have to remember this business of newtons being the unit of weight and force, because weight is a force. Okay, so let's take a look at something here. So let's say we have these two masses stuck together and we're pulling on them. And let's take a look here. So let's say M1 equals, I don't know. We're going to anticipate the lab. So let's say this equals 200 grams, which is then 0.2 kgs. And M1, we can call it 50 grams. And so that's 0.050 kgs. And let's say that F equals 0.5 newtons. Oops. So then we say, what does the acceleration equal to? And in this case, we can see that we're going to have some normal force and some weight that are going to be equal to each other, equal and opposite. So normal force is equal to negative of the weight. So that means sigma F. And let's get in the habit of saying perpendicular equals 0. We say that there's no friction. So then we see that we have the F parallel is simply equal to the F, or the magnitude, if you will, but we already know that it's 0.5 newtons. So we're going to have obviously we're going to have an acceleration to the right, or at least if we say in the same direction of as f. And what is it? So, excuse me, we have f equals ma, and so that we need to put a equals f over m. And what does m equal? Well, the two of them are stuck together, so m equals m1 plus m2. So that's going to be 200. Oh, we need kilograms. 0.200 kilograms plus 0.050 kgs. So then we have 0.52, and we see the newtons. So we have 0.500 newtons divided by 0.250 kgs. And remember, a newton is also a kg meter per second squared. So the kgs cancel out. We get meters per second squared. That's nice. And we notice we punch in numbers to our calculator, and we end up with 2.00 meters per second squared. Huh? Easy peasy. Well, you guys can always stop this. I don't have to wait. All right, so now this is similar to the situation that we have for today's lab, or the upcoming lab. But now, instead of we don't see any force at the moment. We're going to say there's no friction, so we don't have to worry about that. And once again, we have an M1 equal to 0.200 kgs. We have an M2 equal to 0.050 kgs. And so we have a pulley here. If you don't know what that is, you should look it up. And so there's no friction in the pulley either. So no friction here, and no friction with the block in the table. So I don't want to draw too much on here. So in this case, that might point this way, but this is equal to 0. So if we look on this, then we say, what's going on here? Now we say we're on a table, and we have to assume then we're on Earth. So then we know then that there's going to be some weight vector here. And we also see that there's going to be some tension in this string, and we don't know what direction it's pointing. Well, if you think about it, we can imagine that, well, I guess it depends on your point of view, but we can imagine this system's going to move to the right, so we could say this is pointed this way. We might as we'll see in a minute, just leave it like that for the time being. Now, notice how this system, this guy can only be restricted to movement like this, and this one here can only be restricted to movements like that. And in fact, like delta horizontal here is going to exactly equal delta vertical. So any change in this will be 1-to-1. So what that means is that we're allowed to redraw it like this. And so we can look at this and we can say, okay, I remember now there was a weight vector, and that's going to be equal to m2 times gravity. And I suppose, I put the table in there. We have to remember that it's no longer a table, it's just a system. So I suppose what we can do is we can get a little clever here. We can sort of change what that looks like. And so just to remind ourselves that it's no longer on the table. And let's see now. So what we noticed then, that there's also some kind of tension in this rope. So let's take a look at this. So if we look at them individually, so this block, of course, has normal force, has weight of M1, but we know that, and we'll call this 1, those already equal 0. There's no friction. That equals 0. So all we know is that there's a tension pulling it to the right. So that means that the acceleration of F1 is going to be whatever the tension is divided by M1. And the M2 sees the weight of M2, and it feels a force in this direction from the tension. So A of 2 is going to be, and since they're in opposite directions, we can say W, we'll just presuppose from the previous picture that it's going to slide to the right, and it doesn't matter in this grand scheme of things. We'll also, and then divide by mass 2 will get us A2. But here is the leap of logic here. Since one thing we would be told is that the string doesn't stretch. No stretch. String no stretch. So that means that M1 and M2 move together. So the acceleration of M1 plus M2 is just simply going to equal to the force exerted on the system, which is, so if I put them together, the T disappears, and M2, and we simply have this mg. Notice that it's just m2 times g, and that looks exactly like the previous problem. So that means that this is equal to the weight of m2 divided by m1 plus m2. So it's very similar to this problem. So, oops, I should have duplicated this sooner. Let me pause. Oh, maybe we don't have to pause. Now, we have, again, this is 0.200 kgs. This is 0.050 kgs. So we know, then we can calculate, we're going to just use G equals 10.0 meters per second squared. Let's start using a different color just for some relief here. So we know that acceleration of m1 plus m2 is going to equal to the weight of this, which is going to be the mass of m1, 0.050 kgs, times 10.00 10.0 meters per second squared, all over 0.250, because that's when I add up the two masses. And we're going to notice, lo and behold, that we're going to get 0.5 newtons, just like before. And we're still going to get 2 meters per second squared. So typically we would be asked for what is the tension, and then what happens is that these A1 equals A2 equals this, which we calculated was 2 meters per second squared. But you can see now that say 1, 2 equals T over M1, and now we can go ahead, and this is, remember, W1, so then we know that that weight, what was it? That was 0.5 newtons. Oh, I see, we just leave it there. W minus T over M2, and we see we could solve for T, and we could get, let's see, we could find out what T is. But in our case, pause time. So as I was saying, in our case, first of all, let's solve for T. Oops. T equals M1 A12, which is just the A of the whole system, recall. And in this case, M2A equals weight minus T. So that tells me that T equals W minus M2 times A. So then we also know that that's M1 only, no, excuse me, M2 G minus M2A. So, of course, T equals T, so we can say M1A equals M2G minus M2A. And then we can finally remember some force. And in this case, the force that we're going to have is M2 times G, because we're going to have a hanger here, and we're going to put little weights on it, is going to equal M1A plus M2A, which of course is going to equal M1 plus M2 times the total acceleration, which is going to be equal to the total, if you like, so it looks just like the textbook. So now again we have F equals M times this A, and we are going to be measuring A for various M1, M2, and M1. And we're going to measure A in the way we did last time, where we're going to use the time and the S's or X's, whatever you want, the distances, because we're going to be using photo gates again. Okay, so that is the background. all these part of the background, the pre-lab. So your pre-lab, you like to see this derivation, and it's basically that starting with this picture, and we can calculate the total acceleration of the system, knowing the forces, and the only external force is the weight of M2. So then we realized then that that we can then substitute in for the acceleration of each block. Because they're tied together, they have to have the same acceleration, which would be the total acceleration. And then when we see that we can eliminate the tensions because we don't care about the tension. We can create this equation here, and forgetting about that capital F for a minute, we see that we can get M2G equals to some M total times A, and we realize, oh gosh, in this situation, M2 times G is going to be our force, the only available force, because there's no friction using the air track. Okay, there we go.